So weight, mass, and gravity. Let's think about these three things in quite careful ways. Okay, some parts of this are much simplified compared to the way the real world actually works, but it's still useful. Okay, everything is kind of simplified. We can't see everything. If I look at an object, I can't see every electron that it consists of. All I'm seeing is a simplified version, but that doesn't mean it's useless. Let's imagine a person on a planet. Okay, a giant person. Okay, so here's this person, terrible, hulking person on the planet. And what we've got is, because the planet has mass, it means it's got a gravitational field. Okay, that is what we call gravity. And what that does is attract other objects with mass. Now, a person has got mass, which means they also have a gravitational field. But the person is many billions and trillions of times smaller than the planet. I'm just drawing the person like this so we can actually see them. Okay? They're many, many times smaller than the planet, which means their gravitational field is much, much smaller also. Anyway, what we want to avoid talking about is talking about this person and their gravity. Okay? This is their weight. That is a force, and it is force caused by gravity. But the force is weight, brackets, due to gravity. Remember, the gravitational field on the Earth is more or less the same everywhere. So the field on Earth, we use this symbol to represent Earth, is 9.81, but at GCSE we say 10 because it's easier, and it's a decent approximation. Now, if this force was gravity, that would mean that everybody had the same weight, and we obviously don't. Okay, so it's a useful way to make sure we're actually talking about it, and also you need to be used to the kind of language that they're going to use in the tests. Okay, now we know that not everybody has the same weight because not everybody has the same mass. Okay, so the mass of an object is important. Okay, and if you remember, mass is actually an object's resistance to acceleration, and that makes sense. If you pick up a small object and try to accelerate it, usually pretty easy. Picked up a big object, try to accelerate it, usually pretty difficult because of their differences in mass. Okay. Because, you know, if you want to lift something up, we probably don't say, oh, here, would you go accelerate that up for me? That'd be really strange. But you do have to accelerate something to lift it up. You have to give it some certain amount of speed, okay? And also, of course, remember that a larger object is more difficult to slow down, okay, than a smaller object, usually. Depends on the density, obviously. Anyway, we want to talk about how these things relate together. We've talked about mass and gravity. Let's talk about weight. Now, a really useful way to approach any problem in science is think about cause and effect. This is what makes the thing happen, and this is what happens. Okay? So, cause, cook with too much chili. Effect, difficult to breathe. Because, you know, it just it smokes, it kind of vaporizes a little bit, gets into the air. I'm kind of used to it by now, but it's still not very pleasant. All right? Now, the reason I talk about this is it will help you to think about problems very, very clearly between, what makes the thing happen and what actually happens. Because when one changes, then the other is going to change. This might sound very simple, but sometimes people get it a bit wrong. They talk about the effect causing the cause. And the reason I talk about that is weight is the effect, but mass and gravity is the cause. Okay, so without mass, you wouldn't have weight. Without gravity also, you would not have weight. Okay, you would still have mass, okay, but you wouldn't have weight. Okay, so anyway, let's just bring this into the equation. The mass multiplied by the strength of gravity equals the weight. Now, of course, this is different as well. Okay, on Earth we treat it as being more or less the same, even though there's slight differences in different places. Depends how far you are from the Earth's core. But we just treat it as being the same because that works fairly well. Masses of different objects obviously change a bit, but if I could just snap my fingers and find myself in different parts of the solar system, I would have very, very different weights. So of course my weight on the moon, or on Earth, sorry, is just 75 times 10, which is 750. Now if you remember, weight is a force due to gravity. So if you remember, then if it's a force, then weight is measured in newtons and the mass is in kilos. We're not really super worried about the unit for gravity, but it's newtons per kilogram. So it's how many newtons there are in each kilogram, okay? Which means one of my kilograms is 10 newtons. The second one's also got 10. The third has got 10, all the way up to 75. 10 times 75, 750. If I think about my weight on, let's say, the sun. No, I can't remember the amount of gravity on the sun. Let's just do my weight on Jupiter, which is 25 newtons per kilo. 75 times 25, that's a bit more difficult. Let's just do 75 times 5 times 5. So let's just do it. 5 times 5 is 25. 5 times 7, 35, 37. 2 times 5 is 10. 2 times 7 is 14, 15. 18, 75. 1,875. And again, this kind of makes sense because I should be more than twice as heavy on Jupiter, which I think the symbol is like this. Then I should have more than twice the weight. Okay. I would say, guys, have a look at some past paper questions to help you with this, because they don't all ask about this kind of thing. But what you need to recognize is 3 important things. Okay. You need to recognize this equation. You need to recognize that the gravity is different on different planets. And you also need to recognize ways of rearranging this equation. Okay? So, yeah, remember, ask me questions if you're stuck.